most love actually understanding things. So I'm a theoretical chemist, and most of my time is spent doing maths and writing computer software, and understanding why something happens or how a theory works or how a theory describes some chemistry is what makes me tick, basically. Those moments are sometimes few and far between because you spend a lot of time actually reading things, deriving things, understanding things, but when you actually get that click, when you get that moment of understanding, why does this happen or how does it work, that's what drives me. So my research involves designing methods in theoretical chemistry. So that involves creating algorithms, code, software, or equations to describe chemistry in a computer. Two things we're looking at the moment. We generally like to be able to do what are called ab initio calculations. They are, can you calculate all of chemistry in a computer, or maybe just a small molecule and its interactions in the computer? And the really difficult things in that are excited states. So what happens when you, for example, shine light on a molecule? How do you describe that excited state? Now this is really important if you want to capture that light, for example, and harness it, so in photocells and such. Or you can even use it to do chemistry. And the theory behind that and doing that efficiently on a reasonably small computer is very hard to do. So that's one of the problems we're looking at. Another has come through developments in technology at the moment, actually. So there are quantum computers almost available for people to use. And the things that people have been touting them to be able to do is actually quantum chemistry on a quantum computer. That means, can you solve the problems of theoretical chemistry in very short amounts of time? The answer is currently no. We would like that answer to be yes, and we'd like that to be able to be done quickly and efficiently. So we're very interested in algorithms to do that. I mean, in general, very few people in the world have heard of theoretical chemistry or what we do, and very few people actually use it in practice except other scientists. So what we do is design the software and algorithms for other chemists, for example, to use so that they can avoid, in principle, doing the difficult, expensive, toxic chemical reactions, possibly even impossible chemical reactions in the lab. Now, I have said in the past that one of my aims is to sort of put out of business all the experimental chemists and do everything in theory, but we're a long way away from that. So that's the main focus on this. And for example, if you want to look at the world of light capture, there are lots of materials which can capture light, and these have been working very successfully, but they're very limited in their efficiency. And it's possible to design materials that can be far more efficient if we understand what the actual mechanism of that light capture is and how the excited states of molecules can transfer the energy that's harvested into electrons that we can use. And so that's one of the routes that we're working on. Can we model this? Can we then work with experimentalists to design these things and actually solve some of our energy problems?